We have in a tree. We want to answer the queries. Each query contains 2 nodes of how many ways to mark this path from one node to another with 1s and 2s, 1 plus 2 plus 1, to make them odd. Number of ways. Imagine the simple problem of just single query. We want to find the length of this path. This is first. Then we define the number of odd ways to mark them as subproblem of the previous one. So ways of n equals, and this is like odd, equals ways of n minus 1 of even plus ways n minus 1 of odd. Why is that? It's because we can add for the even to make odd, we're doing plus 1, and for the ways of odd to stay odd, we're doing plus 2. This is how it can be simplified to just 2 to the power of length. That's one subproblem. Then the second subproblem is for the big tree and big number of queries. Find the length of the shortest path. They both together and okay, n equal 10 to the power of 5 and queries equal 10 to the power of 5. They should be optimized. For optimization, we use lowest common ancestor. This can be found by defining the parent of each node or with some tricks like time trick in depth first search. Imagine we have depth first search, and for this node, when we enter it, we mark it in of this node equals time plus plus, and when we exit it, we're doing out x equal time plus plus, and then we can say that if the time of in and out of two nodes are intersecting, then they are in the common ancestor, and if they're not, then the common ancestor is something to the up of they both together. Okay, that is the half of the problem of the shortest path, but the trickiest trick is the binary lifting, and without the binary lifting you can't solve this problem at all. It would give till time limit exceeded. So binary lifting, imagine we have to jump from this node one step, and we say this is a 2 to the power of 0 jump, and if we want to jump 2 steps, it is 2 to the power of 1 jump, and if we want 4 steps, it is 2 to the power of 2 jump, and if we want 3 steps, it is 2 to the power of 2 plus 2 to the power of 0. This is 3 steps. Or not, this is 1, 2 to the power of 1. Okay, this is how we can do this jump in a binary lifting way. So imagine we define this up jump for the X node, and we fill in it for each possible powers of 2. E is from 0 to 20, but basically it is 2 to the power of 0, 2 to the power of 20, and it is up of I minus 1, and this is previous step of the same node, I minus 1. Basically this is half. Because I minus 1, it is the range divided by 2. This is powers. Okay, now let's look at the code. This was my accepted version. You have to precompute the powers of 2, because to not do n squared accidentally. I use the depths, and I use this binary lifting. To define ancestor, I use time to enter, time to out. If they're already ancestors, just return it. If they're not, go up. And while it's not, we're doing up from the largest power of 2, so the bigger jump goes first, then smaller. So we're checking this. If the jump is not overshooting, that we do the jump. This is how it sounds. And for the timing, we use a depth first search. I called it fill, and this is time to enter of this node, time to out from this node. To later compare this time to enter, the A was first and A was last to out. So we are inside of A. Okay, that's how the code looks. Let's look at more short version. This is Kotlin, just inlined everything. And the Rust for the different approach of the breadth first search. This doesn't allow us the time trick. We have a defined ancestor. We use depths instead, and then we do like checking this depth A, depth B, then we find this difference of depth to do these jumps in binary representation order, and then we do finally binary lifting. So this is from the biggest jump to the smallest one. Okay, that's it for today.